Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into fraud detection, the system that decides whether a transaction, login, or account opening is legitimate or fraudulent in milliseconds. We'll cover how companies like Stripe, PayPal, Shopify, and banks combine rules, machine learning, graph analysis, and a feature store to stop fraud without blocking real customers. Whether you're preparing for a senior engineering interview or building risk infrastructure at scale, this one is for you. Let's get into it. Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into fraud detection, the system that decides whether a transaction, account sign-up, or payment is legitimate or fraudulent in milliseconds. If you have ever wondered how companies like Stripe, PayPal, Shopify, Uber, or banks stop stolen cards, fake accounts, bot attacks, and collusion rings without blocking real customers, this video is for you. We'll walk through the functional requirements, non-functional requirements, system architecture, end-to-end user journey, core models, low-level design, and the trade-offs that show up in every senior system design interview. Whether you are preparing for a FANG interview or building risk infrastructure, let's get into it. Here is the core problem. A digital business processes millions of transactions, logins, payouts, and account openings every day. Hidden inside that traffic is a small but dangerous percentage of fraud. Stolen credit cards used to buy goods, synthetic identities opening accounts, bots testing credentials, merchants colluding to steal refunds, and friendly fraud chargebacks. The business must stop bad actors before money moves or goods ship, but it cannot inconvenience legitimate customers with false declines. Fraudsters also adapt fast, so a static rulebook quickly becomes useless. The challenge is to build a real-time detection system that is fast, accurate, adaptive, and explainable. Let's walk through the functional requirements. First, the system must ingest high-volume events such as payments, logins, sign-ups, account changes, and device fingerprints from web, mobile, and back-end systems. Second, it must evaluate a configurable rule engine that encodes known fraud patterns, like velocity limits, blacklisted devices, unusual geolocation, or mismatched billing data. Third, it must run machine learning inference to compute a risk score for every event, using behavioral and historical features. Fourth, it must support graph analysis to detect collusion rings, shared devices, money mule networks, and account takeovers. Fifth, it must provide a feature store that serves fresh, consistent features for both online decisions and offline model training. Sixth, it must make a decision: approve, decline, step-up authentication, or send to manual review. Seventh, it must manage cases, feedback loops, and model retraining so the system improves over time. These capabilities are what make fraud detection operational, not just predictive. Now the non-functional requirements. Latency is the most critical constraint. A payment decision must complete in tens to a few hundred milliseconds, or the checkout experience breaks. Throughput must be massive, handling thousands of events per second with spikes during sales or launches. Accuracy must be high on both dimensions. We need high recall to catch fraud, and high precision to avoid false positives that anger customers. The system must scale horizontally because fraud volume grows with business volume. Explainability matters because analysts, regulators, and customers demand reasons for declines. Security is paramount. Model artifacts, feature data, and decision logs must be protected. And availability must be extremely high because every blocked decision is lost revenue. Here is the high-level system architecture. On the left, event producers stream transactions, logins, and account activity through a load balancer and API gateway into a Kafka ingestion layer. A stream processor enriches events with device, geo, and behavioral data, then evaluates rules and features in near real time. The feature store serves low-latency features to the rule engine and the machine learning model service. The model service runs inference and returns a risk score. A graph engine analyzes relationships between accounts, devices, and payments to detect collusion. A decision service combines rule outcomes, model scores, and graph signals into a final decision. A case management system stores alerts for analysts, collects feedback, and triggers model retraining. An analytics backend tracks performance, drift, and business impact. The key metrics to memorize cold. Fraud detection rate, also called recall, the percentage of real fraud caught by the system. False positive rate, the percentage of legitimate transactions incorrectly blocked or stepped up. Precision, the fraction of flagged events that are actually fraud. Chargeback rate, a downstream business metric that reflects missed fraud on card payments. Average decision latency, the time from event arrival to final decision. Model drift, the change in feature distributions or model performance over time. And case review efficiency, the fraction of alerts correctly resolved by analysts. These metrics are what the business, risk team, and regulators actually care about. Let's trace the end-to-end user journey. A customer enters payment details at checkout and clicks pay. The fraud detection system receives the event, fetches the customer's recent behavior, device reputation, and merchant history from the feature store. The rule engine flags a velocity spike. 3 different cards were used from the same device in the last hour. The machine learning model returns a risk score of 87 out of 100. The graph engine adds that the device is linked to a previously suspended account. The decision service declines the transaction and requests strong authentication. A case is created automatically for the risk team. The next morning, the analyst confirms the fraud, labels the device, and retrains the model. Within hours, similar patterns are blocked with higher confidence. The core models and algorithms. The rule engine evaluates deterministic fraud signals, such as velocity limits, blocked lists, and geo-impossible travel. The machine learning layer uses gradient-boosted trees, logistic regression, or neural networks trained on historical labels to produce a calibrated risk score. The graph engine builds an entity graph of users, devices, cards, IP addresses, and merchants, then runs community detection or label propagation to find fraud rings. Entity resolution links multiple identifiers to the same real-world actor, even when explicit IDs differ. The feature store provides point-in-time correct features for both training and serving. The decision engine combines scores into a final action with thresholds that can be tuned by segment. The feedback loop moves confirmed outcomes back into training data and adjusts model weights. The key trade-off is precision versus recall. Catching more fraud usually means more false positives. Now the low-level design deep dive. The online pipeline is implemented as a low-latency DAG. An event enters the gateway, is validated, and is routed to feature enrichment. The feature store lookup uses a key value store like Redis for online features and a column store for batch features. The rule engine runs in a stateful stream processor and updates sliding window counters. The model service loads the latest model into memory and returns a score in single-digit milliseconds. The graph engine stores relationships in a graph database and runs pre-computed risk aggregations. The decision service applies a policy matrix that maps score bands and rule triggers to actions. A decision log table records every input, feature, score, and reason for auditability. The offline pipeline uses a feature engineering job, training pipeline, model registry, and shadow deployment to safely update production models. Key takeaways for your interview. First, fraud detection is a real-time decision system, not just a machine learning model, so emphasize latency, throughput, and the decision service. Second, always separate rules, models, and graph signals, and explain how they combine into a final score. Third, the feature store is the heart of the system because it connects historical behavior to online decisions. Fourth, graph analysis is what catches organized fraud and collusion that individual models miss. Fifth, feedback loops and model governance are essential because fraud patterns change continuously and regulators demand explainability. If you can walk through this system with these 5 points, you will signal strong senior-level design thinking. That's it for fraud detection. If this helped, like and subscribe, and I'll see you in the next one at Cloud Wizard. And that's a wrap on fraud detection. We covered the full picture, from event ingestion and real-time scoring, through rules, machine learning, graph engines, feature stores, and the low-level design of the online decision pipeline. If this video helped you, please hit that subscribe button and the bell icon so you never miss a new system design video. Drop your questions in the comments below. I read every single one. See you in the next one at Cloud Wizard.